Welcome to Maths with EJD. Starting from the last video, we started looking at non-linear programming, right? And we said that there's different methods we can consider for non-linear programming, like the penalty and barrier methods. Actually, they go together, but I have decided to split them up here for better understanding. So in the last video, we looked at penalty method. Now we want to consider barrier method, and later on, we'll be looking at the KKT conditions, which is a generalization of the Lagrange multiplier method. And then we are going to also look at the evolutionary algorithms. Evolutionary algorithms. Okay. The evolutionary algorithms involve algorithm based on genetics, based on metallurgy and all of that, like genetic algorithm, uh, uh, simulated annealing, and all the rest of them. So we've considered penalty method. So let's go for barrier method this time around. Barrier method. So you can see it as a continuation of the penalty method because after imposing a penalty on the objective function of a non-linear problem. So the barrier method helps to guarantee because the penalty method can become very large, but the barrier method ensures that no matter how large things become, the solution is constrained within the feasible region where the solution is. So the objective is to learn how the barrier method transforms constrained optimization problems into easier unconstrained ones by using a barrier term to prevent constraint violations. But penalty method penalizes constraint violation, but barrier method actually prevents it. So first thing, let's look at um let's look at an introduction to the barrier method. Okay, so the barrier method converts constrained optimization problems. And we have seen methods for solving them previously, like Lagrange multiplier, sequential quadratic programming, and interior point method. So some of them are still coming back here. So the barrier method converts constrained optimization problems into unconstrained ones by adding what you can call a barrier, by adding a barrier that prevents the solution from violating the constraints. So instead of penalizing, instead of which happens for penalty method, right? Instead of penalizing violations after they occur, after they occur, as in the penalty method, that's what happens in the penalty method. So violation occurs and penalty method penalizes it. As in the penalty method, the barrier method actually prevents, the barrier method prevents them by making the objective function, by making the objective function infinitely large, infinitely large, near near the boundary, near the boundary of the feasible region. Okay, so this makes it impossible for the for any kind of violation in the first place. It's more like erecting a very high fence that nobody can scale, basically. Okay, so number two, let's talk about general form. General form of the barrier method. Of the barrier method. Okay, so for inequality constraints, for inequality constraints, the barrier function, the barrier function is b of x comma mu equals f of x, that's the objective function, minus mu summation from I equals 1 to m, then you have log minus gi of x. Of course, I mean, from the very nature of log, right? Log of a negative expression is going to be infinite, so you're never going to get out of that loop. Okay, so that is what happens right here. Of course, we're going to explain the terms. We have the like mu. Obviously, that should be the parameter, right? So where we have mu, mu is a positive, it is a positive scalar controlling, it's a positive scalar controlling the strength of the barrier. So it is analogous to the penalty parameter we saw the other time. So this one is more like the barrier strength or barrier parameter, if you like. Then we have gi of x less than or equal to 0, which are are usually the inequality constraints. Inequality constraints. Okay. Then we now have log, right? We have log of minus gi of x. That's the actual barrier now. Minus log gi of x, which makes the barrier term, grow large as gi of x approaches 0. You know, log of 0 is undefined. Okay, so it makes the barrier term grow large as gi of x approaches 0, forcing the solution, forcing the solution to stay inside the feasible region. Okay. All right. So we are due for an example. Let's go for that. I'm gonna switch to this and say this. So example. So we want to minimize f of x equals, of course, that should be like f of x1, x2 more properly, but let me just leave it that way. But we just know x is more like a vector. So f of x equals x1 minus 2 squared plus x2 minus 3 squared. I think the same thing we did before. Now subject to g1 of x equals x1 plus x2 minus 4 less than or equal to 0. So in this case, uh we have just the inequality constraint. So step one in that situation, step one is to want to define the barrier function, define the barrier function. Since we know g1 of x, so the barrier function is easy to define. So we first write the objective function, which is f of x equals x1 minus 2 squared, x1 minus 2 squared plus x2 minus 3 squared, and the inequality constraint, which is g1 of x equals x1 plus x2 minus 4. Okay, so from there, the barrier function becomes b of x comma mu, and that is equal to x1 minus 2 squared plus x2 minus 3 squared minus mu log 4. Yeah, log 4. This is more like we're transforming it into, this is supposed to be like, supposed to be like 0, right? So this expression now, we are transforming it into something like the other side. So that'll be like 4 minus x1 minus x2 equals 0, or 4 minus x1 plus x2 in brackets equals 0. So this is what we are bringing down here. So that is 4 minus x1 plus x2, like this. So that is the barrier function right there. I want to encircle that to show how important that is. Okay, so with that done, we can go for the next step since you have now written the barrier function. So we go for step 2. So in step 2, we choose a barrier parameter. Just like we chose a penalty parameter before, choose a barrier parameter. We choose a barrier parameter. So here again, let's choose the same thing. Let's choose a barrier parameter mu equals 10. Okay, so the barrier function becomes b of x comma 10, which is x1 minus 2 squared plus x2 minus 3 squared minus 10 into log 4 minus x1 plus x2, like that. And that takes us to step 3. I want to make this one also fanciful. So step 3 now. So we have chosen the barrier parameter. So step 3, we evaluate the barrier function. Evaluate the barrier function for some points, just like what we did for penalty function the other time. So do this for some points. So now let's evaluate the barrier function. Let's evaluate the barrier function at a few points. Again, you want to make that as close as possible to look at the expression you have. The original x1 minus 1 squared plus x2 minus 3 squared. So you want to make the values something close to 2 and 3, maybe 1, 2, 3, 0, like that. So again, before we used 2, 2, and 3, 2. So we can go for this again. So now let's say, or should I just change color here? Let me go back to this. So let's say A now. We say for x equals 2, 2. That's x1 is 2, x2 is also 2. That's what that means. So f of x is simply 2 minus 2 squared plus 2 minus 3 squared, which is 2 minus 2 is 0. 2 minus 2 is 0 squared is 0. 2 minus 3 is minus 1 squared. That's 1. And that just evaluates to 1. So we have that for f of x, comma y, or f of x1, x2. Then we have the inequality constraint, which is now x1 plus x2 minus 4. That is simply 0. So there is no violation. So there is no violation. There's no violation of the constraint. Okay. So since there's no violation of the constraint, right, we can go right back and say, therefore, the barrier function, evaluates to b2 to 10, which is, of course, f of x is 1. So we have 1 minus mu is 10 into multiplied by the log of 4 minus x1 plus x2. That's 4 minus 2 plus 2, like that. So that means this is the same as 1 minus 10 log 4 minus 4. So that means we have 1 minus 10 log 0. Log 0 is undefined. So that's a big one. So b of 2 comma 2 10 is equal to 1 minus 10 log 0, which is basically infinity. So you cannot cross the boundary. Okay. So with that done, let's try another point. We've done 2, 2. Let's do something else. Say, let's do b, which is, let's say, for x equals 3 over 2, comma 2. That means x1 is 3 over 2 and x2 is 2. So here we say f of x is equal to 3 over 2 minus 2 squared plus 2 minus 3 squared. 3 over 2 minus 2, that's like 1.5 minus 2. That's minus 1 over 5. Minus 1 over 5 squared is 1 over 25, right? No. This is 1.5 minus 2. That's 0.5, yeah. That's minus half. So we can say this is minus 1 over 2 squared, okay, plus 2 minus 3 squared, that's 1 squared again. So this is simply 1 over 4 plus 1. So that is 5 over 4, which is simply the same thing as 1.25, 1.25. So f of x is 1.25. If we do that, then we can have g1 of x. Again, g1 of x is x1 plus x2 minus 4. That is x1 here is 3 over 2, x2 is 2 over 1 minus 4 over 1. So that is 2 LCM. So that's 3 plus 4 minus 8. That is simply 7 minus 8, which is minus 1 over 2, which is minus 0.5. I can bring that down. We have that g1 of x is equal to minus 0.5, like that. So we can then do the barrier. Therefore, the barrier function evaluates to b of 3 over 2 to 10 equals f of x is 1.25. This is what we got up here. F of x is 1.25. Then minus the barrier is 10. Then log, so we have log 4 minus x1, which is 3 over 2 is 1.5. Let me just write 3 over 2 plus 2. Okay. So we can work with this. This is 1.25 minus 10 log 4 minus 1.5 plus 2. That. So that's 1.25 minus 10 log 4 minus 3.5. So this is 1.25 minus 10 log 0.5. Okay, so we have 0.5. Then, I did not make any statement about it. This is minus 0.5, right? So of course we can talk about this, that this implies, so we can say, so there is no violation of constraints, because that's actually supposed to be less than or equal to 0. So it's okay because minus 0.5 is less than 0. So there's no violation of the constraint. So then we can now come over and try to evaluate the barrier function, which we are on already. So this is 1.25 Okay, 1.25. And this is, we can say this is minus 10. We can use some logarithm things here. So minus 10 log, this is 5 over 10, or this is 1 over 2 in short. This is 1 over 2. Okay, so this is 1.25 minus 10 log. 1 over 2 is the same thing as 2 raised power minus 1. Okay, so, and from the law of logarithm, the minus 1 can come back. So we have minus 10 into minus 1 log 2. Okay, so this is 1.25 plus 10 log 2 plus 10 log 2. Okay, so log 2 is 0.693 if you punch your calculator. So 1.25 plus 10 into 0.693, thereabouts. So we have 1.25 plus 6.93. So with that, now we have 5 plus 3 is 8. 2 plus 9 is 11. So we have 1. Then we have another one to carry over there. So this is 8.18. So in all, we have that B of 3 over 2 to 10 is equal to 8.18. So this is not so large, right? So what this teaches us is that here, the barrier term, in this case now the barrier term is not infinite like the other case. The barrier term is finite. Okay, it's not infinity, and the solution is feasible, and the solution is feasible. So as x1 plus x2 approaches, as x1 plus x2 approaches 4, the second constraint is that x1 plus x2 is minus 4 is less than or equal to 0. So as these two approaches, as what x1 and x2, x1 plus x2, the sum, as this sum of x1 and x2 approaches 4, so we say that the logarithmic term increases significantly, because when it's at 4, it becomes 0, and log of 0 is undefined. So the logarithmic term increases significantly, pushing the solution, away from the boundary. Okay. So with that done, we can talk about step 4. Step 4 now is where we minimize the barrier function. Minimize, just like we also minimize the penalty function, minimize the barrier function. Okay. So here, to minimize the barrier function, we would apply an unconstrained optimization algorithm, which, I mean, we've done most of this before: gradient descent, Newton's method, conjugate gradient, and the rest of them. We would apply an unconstrained optimization algorithm, right? So as the barrier penalty mu decreases, so in the case of penalty parameter, it has to be increasing, right? As mu decreases, the barrier becomes less restrictive, and the optimization can converge to the optimal solution, while maintaining feasibility. Okay, so let's talk about some key points Yeah, let me just call this key points generally. Key points, just like we saw key points for penalty parameter, for penalty method. So first of all, the barrier method, the barrier method prevents violations of inequality constraints, So you remember that penalty method worked for both inequality and equality, but here, this one is just for inequality. So the barrier method prevents violations of inequality constraints by introducing a large barrier, a large barrier as the solution, as the solution approaches the boundary. Okay, that's one point. Another point would be that it is particularly, so you see that here we've not talked about equality constraints. It is particularly useful for inequality constraints. So that's why we didn't bother about equality constraint. For inequality constraints, but cannot be directly applied. It cannot be directly applied to equality constraints. Okay. So that's why we didn't bother about equality constraints in this case. And then we have the third point. Okay. As mu decreases, I think we've said this before, as mu decreases, the barrier, okay, I think it's the same thing I've just said. The barrier becomes less restrictive, less restrictive, allowing the algorithm, to converge to an optimal solution. Okay. Now, since we just tested things the other time, we're supposed to solve a problem properly, and then I'm just going to talk about the Python solution to the problem. Okay. So again here, this is the barrier method in Python. Same thing like before, we have the same expression, and this time around, the focus is on the inequality constraint. The equality constraint is not so important, is not really uh, at work here. So it's everything is about the same except that no equality constraint because barrier method works better for inequality constraints. So I mean, you can sort of the code, you can get it on Facebook, copy it out into your IDE and try things out for yourself. So in this case now, based on what we have seen before, you discover that the solution, so you see that for the optimal solution, x1 is 1.4999, x2 is 2.4999. So it's more like x1 is 1.5 and x2 is 2.5. And then you can see how where this is located here. So x2 is like 2.5 while x1 is like 1.5, somewhere around here. So like if you trace it down this way, like 1.5 around here, 2.5 around here. Interesting thing is that 1.5 and 2.5 added together will give us that 4, which is the boundary we're talking about. So 1.5, 2.5 is like 4. And the objective value at the optimal solution, that's if you put this into the expression, the original expression, you get something like 0.5. So let me go back and put this in the original expression so we can see how this uh, comes about. Okay. So let me use this now. From the Python code, okay, x1 is equal to 1.5 approximately, okay, and x2 is approximately 2.5. So if we put that into, so we can say, so f of x1, x2, or what we just called f of x before, that was x1 minus 2 squared, if I remember very well. Yeah, I think so. Yeah, x1 minus 2 squared plus x2 minus 3 squared. Okay, so x1 minus 2 squared plus x2 minus 3 squared. So this is more like this is like 1.5 minus 2 squared plus 2.5 minus 3 squared. This is minus 0.5 squared plus minus 0.5 squared. Okay, so this is like 0.25 plus 0.25, and that is simply 0.5. So we see that we see that x1 is 1.5, x2 is 2.5, and minimum value of f of x1, x2 is equal to 0.5, just like we got from that code. Okay, so let's move on and talk about practice questions now. So let's talk about some practice for barrier method before we call it a date. Of course, I mean, talking about both methods, right? Penalty method adds penalty terms to constraint violations. For constraint violations, which grow larger as violations increase, making the problem easier to solve unconstrained. Then barrier method introduces a barrier function that becomes infinitely large as the solution nears the constraint boundaries, preventing constraint violations. Both methods are effective for converting constraint problems into unconstrained ones, though they differ in their approach to handling the problems. So let's look at this. Okay, I mean, just one question, I think. So want to minimize f of x1 comma x2 equals x1 minus 1 squared plus x2 minus 2 squared, subject to g of x1 x2 x2 equals x1 plus x2 minus 3 is less than or equal to 0. So in this case, of course, you don't expect equality constraint because barrier method doesn't work very well with equality constraints. So what you are supposed to do now is, number one, write the barrier function. Write the barrier function for this problem using a barrier parameter. Mu equals 10, just like we did before. Mu equals 10. Number two, the next second task for the same problem. So you want to evaluate the barrier function. Evaluate the barrier function at the points 2, 1 and 1.5, 1.5. Okay, but don't forget to use the Python code too freely. You can get it on Facebook, like I said. And you want to discuss the behavior of the barrier function. Discuss the behavior of the barrier function at the boundary of the feasible region. Okay. So that's it. That's the end of barrier method for solving nonlinear programming problems. In the next set of videos, I'll be talking about the Karush-Kontuka conditions, which is a generalization of the Lagrange multiplier method, right? So you want to watch out for that. So let me feel free to let me see your answers to this practice on Facebook or on YouTube. You can get the code on Facebook, like I said already. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Let me also know if there's how helpful these videos are for you, right? Let me know. Then if you have subscribed, thank you. If you have not subscribed, please go ahead and do that. And everybody, don't forget to subscribe, to hit the notification bell so you can always get alerted each time a new video is released. Then also like and share so that more people can have access to this great content. So like, come your way again, keep doing maths right. Bye.